All right. In this session, we're going to talk a little bit about performing mathematical operations on rational expressions. Rational expressions we introduced in the last segment. This will be operations on rational expressions, and specifically multiplication, division, and addition and subtraction. Sections 6.2 and 6.3 of your textbook for those of you following along. So I'll start out with the easier set, which is multiplying and dividing. And it kind of works like fractions. Multiplying and dividing is a bit easier, and adding and subtracting is a little bit more complicated. So just like when you're multiplying fractions, to multiply two fractions, you multiply the numerators together, and you multiply the denominators together. Same sort of thing works with rational expressions, only then there might be a bit more simplification in the process. And I'm just going to dive right into a few examples of working with these things. This is example 1 off of page 324, where it asked to multiply the following and simplify and identify the non-permissible values. So what we are being asked to multiply is a squared minus a minus 12 over a squared minus 9 multiplied by a squared minus 4a plus 3 divided by a squared minus 4a. Now, your first step in just about anything to do with rational expressions that you're going to perform operations on is to factor. Step 1, factor. That makes life much easier for a lot of these sorts of questions, to factor before you get underway. So, for the quadratic, a squared minus a minus 12, that one factors nicely into a minus 4 times a plus 3. A squared minus 9, the difference of perfect squares, factors into a plus 3 times a minus 3. A squared minus 4a plus 3 factors into a minus 3 and a minus 1. A squared minus 4a you might stare at for a little bit. The factoring in that case, though, is just a case of simple factoring, and I can bring the a out of both expressions, and it becomes a times a minus 4. So now, the end result of all that is I have a minus 4 times a minus 3 times a minus 3 times a minus 1 divided by a plus 3 times a minus 3 times a minus 4. So now that everything is multiplied in the numerator and multiplied in the denominator, you can start to think about whether anything cancels. I can't talk about canceling things up here, because these are a bunch of groups of addition and subtraction, and I can't just take chunks and cancel things out. You might see the two a squareds here, and for instance think, oh, I can just cancel those out. No, don't do that. That doesn't work. A squared minus a minus 12 divided by a squared minus 9 is very different than negative a minus 12 over negative 9, for instance. Things need to be factored. You need to have everything multiplying together in the numerator and in the denominator before you can talk canceling. Now, before you cancel anything from this, I'll jump into step 2, which would be look for the non-permissible values. Anything that's going to lead you to a division by 0 is non-permissible. And in this case, that would be negative 3, positive 3, 0, or 4. So A cannot equal negative 3, positive 3, 0, or 4. I like to kind of find those at this point, because if you start canceling things out, then you start to lose track of where your non-permissible values are. Now, I can cancel things. Step 3, cancel. I should say divide to 1, but I'm going to go short form and say cancel. A minus 3 divided by A minus 3 is 1. A minus 4 divided by A minus 4 is 1. What that leaves me with is A minus 3 times A minus 1 over A plus 3 times A. You can have that. Oh, look what I did. This is a plus up here, which I changed to a minus. Look at me go. So this A minus 3 would cancel with this one. This A plus 3 would cancel with this one. And what I'm left with is just A minus 1 over A. And then step 4, finally, final statement. What this lets me say is that A squared minus A minus 12 divided by A squared minus 9 times A squared minus 4A plus 3 over A squared minus 4A is equivalent to A minus 1 over A, so long as A doesn't equal negative 3, 0, 3, or 4. And there it is. We've multiplied two rational expressions together. I want to stress again, factoring early on really makes life a little bit easier as you go through. Now example with dividing. Dividing just ends up with one extra step in it from multiplying, which I'll show as I go through the example. It's example 2 on page 325, where I'm doing the division. X squared minus 4 divided by x squared minus 4x divided by the rational expression x squared plus x minus 6 over x squared plus x minus 20. Still going to start out the same way. I'm going to factor. The perfect square, x squared minus 4, becomes x plus 2 times x minus 2. In the x squared minus 4x, I can only factor out the x, divided by x plus 3 times x minus 2, all over x plus 5 times x minus 4. Now that I've factored everything, I can start to talk a little bit about non-permissible values. I can't be dividing by 0 any place, so that means x can't be 0 or 4 or negative 5. But I might have to add a couple more to this, and I'll show why in a second. So I've factored, step 1. I look for non-permissible values, my step 2. But now I've got a new step 3. And that is change any division to multiplication by the reciprocal. So the same way that you can think of dividing by 2 is the same as multiplying by a half. Division by any rational expression can be written as multiplication by the reciprocal. So I can rewrite this as x plus 2 times x minus 2 over x times x minus 4 multiplied by x plus 5 times x minus 4 over x plus 3 times x minus 2. Now I've got a couple of other places to look for division by 0 problems, and I end up adding that x also can't equal 2 or negative 3. But now that it's all a big string of multiplication, I can think about things that I can cancel. X minus 2 divided by x minus 2 is 1. X minus 4 divided by x minus 4 is 1. There's nothing else left to cancel. So then this reduces to, and I'll just start by writing it out, x squared minus 4 divided by x squared minus 4x, all that divided by x squared plus x minus 6, or x squared plus x minus 20, would be equivalent to x plus 2 times x plus 5 over x times x plus 3, so long as x does not equal negative 5, negative 3, 0, 2, or 4. And sometimes you can get a few different things buried into one setup. So I'll do an example which has some multiplication and some division involved. This is example 3 from page 326. And we need to simplify 2m squared minus 7m minus 15 divided by 2m squared minus 10m divided by 4m squared minus 9 over 6 times 3 minus 2m. So again, I'm going to start with factoring. 2m squared minus 7m minus 15 from your factoring rules from before would be equivalent to 2m plus 3 times m minus 5. The 2m squared minus 10m, I could factor a 2m out of each term to leave me with m minus 5, divided by the perfect square here, 3m squared minus 9, or sorry, the difference of perfect squares there, I could rewrite as 2m plus 3 and 2m minus 3. The 6 in the denominator stays a 6. And I multiply by, and I might rewrite this as 3 minus 2m over 1, just to keep everything looking like a fraction. So immediately, I've got non-permissible values of 0 and 5. And then I'm going to change any division to multiplication of the reciprocal. That's going to lead me to a couple more non-permissible values. M can't equal negative 3 halves or positive 3 halves. Then I look for any divisions that give me a 1. 2m plus 3 divided by 2m plus 3 is 1. M minus 5 divided by m minus 5 is 1. Now, the thing to be careful about here, 3 minus 2m and 2m minus 3, while not exactly the same, are negatives of each other. So 3 minus 2m divided by 2m minus 3 would give me negative 1. So then out of all that, I end up with negative 6 over 2m. 6 over 2 can easily simplify to 3 over 1, so this whole thing becomes negative 3 over m. And then I can say that 2m squared minus 7m minus 15 over 2m squared minus 10m divided by 4m squared minus 9 over 6 times 3 minus 2m is equivalent to negative 3 over m, so long as m doesn't equal negative 3 halves, 0, 3 halves, or 5. That's my equivalence right there. Alright, those are a few examples of multiplication and division, which are relatively straightforward. In adding and subtracting, we get a little bit more complicated, and I'm going to do a couple of examples of working with some of those. So, if I think to fractions, generally, if I want to add two fractions or subtract two fractions, they need to have the same denominator. So that's what's going to be the trick in this, is making sure that my fractions have the same denominator. If I look at example 1, on page 333, we're asked to work out the sums and differences given. So my first one is 2a over b minus a minus 1 over b. These both have the same denominator, so I can simply subtract across the numerator. One thing that I will mention though is you're subtracting everything in here. If you're not sure, you can stick brackets around this to make yourself concrete on that. 2a minus a is a. No ones minus negative 1 leaves me to plus 1 over b. So this is a plus 1 over b, and b can't equal 0. Parts b and c of this are very similar, because this example has everything with the same denominator. 2x over x plus 4 plus 8 over x plus 4 is just going to end up equaling 2x plus 8 over x plus 4. I can factor that numerator to 2 times x plus 4 over x plus 4. It's worth noting from there that x can't equal negative 4. And then I divide, and I can say that that whole thing equals 2 so long as x doesn't equal negative 4. And then lastly, I have x squared over x minus 2 plus 3x over x minus 2 minus 10 over x minus 2. Since my numerators are all the same, this is the same as x squared plus 3x minus 10 over x minus 2. The numerator, cut off a little bit there. That's supposed to have the x equals negative 4. Can't equal negative 4. Alright. So x squared plus 3x minus 10 over x minus 2 will factor into x plus 5 times x minus 2. My x minus 2's cancel, and this whole thing is equivalent to x plus 5 so long as x does not equal positive 2 because of the division there. So again, when your denominators are all the same, addition and subtraction is pretty straightforward. But when they're different, you've got a little bit more work to do. That takes us to example 2 on page 334. So in this one, we're asked to add 2x over xy plus 4 over x squared minus 3. So, nothing there with the denominator that's the same. Although, I will say that if you're going to add and subtract fractions from each other, or rational expressions, it's good to make them all rational expressions. And we're going to write that 3 as 3 over 1. So I need everything here to have the same denominator, and I'm going to try to do that in as simple a way as I possibly can. Now that means that each of my denominators has to have at least an x in it, at least a y in it, and at least an x squared in it. So my easiest way to do that is to multiply my first expression by x over x. That would give me 2x squared over x squared y. My second expression, I'd multiply by y over y. X squared y, and the 3, I'd multiply by x squared y in both the numerator and denominator. Now, they all have the same denominator, so I can combine them all at this point, and I'd get 2x squared plus 4y minus 3x squared y over x squared y. I don't believe anything in that numerator factors nicely, so I really can't simplify this any more than this. and I've got non-permissible values at 0 for x and 0 for y. So again, if my denominators are different, I've got to choose some multiplication that will make the denominators all the same so I can combine them. Part B of this, combining y squared minus 20 over y squared minus 4 plus y minus 2 over y plus 2, and that's what I'm trying to combine. Again, factoring your numerators can be quite helpful, your denominators. There's not much point in factoring the numerators before you've combined everything. But this tells me when it's factored, I already have a y plus 2 in the denominator in both fractions. So all I really need is to get a y minus 2 in here. So I don't need to change my first expression. My second expression I could multiply by y minus 2 over y minus 2. Wondering if I have enough room. I'll start over here. So my first expression stays the y squared minus 20 over y plus 2 times y minus 2. It's easiest to add these if your numerator is all expanded out. So that's going to be y squared minus 4y plus 4 over y plus 2 times y minus 2. And now I can add across. And I'd end up with y squared plus y squared, which is 2y squared. No y's minus 4y's, 4y. And negative 20 plus 4 is negative 16 over y plus 2 times y minus 2. The top of this factors into, I can bring a 2 out of everything to get y squared minus 2y minus 8 over y plus 2 times y minus 2. And this factors a little bit further into being y minus 4 times y plus 2 over y plus 2 times y minus 2. So at this point I know that my y values that are non-permissible are plus or minus 2. The y plus 2 divided by the y plus 2 goes to 1, and my expression is equivalent to 2 times y minus 4 over y minus 2, so long as y does not equal negative 2 or positive 2. Common denominators. If you're going to add or subtract these fractions, they have to have a common denominator first. I'll do one more example, and it's the sort of example that people first look at and scream and try to run away. But it's not too bad if you follow along the rules of math. And this is part C from that same example, so this is still example 2 on page 334. And example C has us combining 1 plus 1 over x divided by x minus 1 over x. It's also telling us what our non-permissible values are, although we could kind of figure those out. X can't equal 0 because the division by 0 here, or plus or minus 1 because that would leave me with division by 0 here. Okay, so as I mentioned, if I'm going to add or subtract fractions, I'm going to start by writing everything out as a fraction. So, to combine the addition in my numerator, I'm going to make sure these both have a denominator of x. And the same thing for the denominator. X squared over x minus 1 over x. Now I can combine my fractions in both the numerator and the denominator. It'll be x plus 1 over x, and then x squared minus 1 over x. And as we said before, we can change division to multiplication by the reciprocal. I see there is something there I can factor. The perfect squares here on the bottom can factor to x plus 1 times x minus 1. I already know what all my non-permissible values are, so I can just cancel things out. X divided by x is 1. X plus 1 divided by x plus 1 is 1. One of the more common mistakes I'll see people make is if they cancel out everything in the numerator and they're just left with this division, they would just write it as x minus 1. And that's a big no. Doesn't work that way. There's still a 1 implied in this numerator, so this would be the same as 1 over x minus 1. And ultimately, I can say that 1 plus 1 over x minus 1 over x is equivalent to 1 over x minus 1 so long as x does not equal 0 or plus or minus 1. So there's been a few examples of performing mathematical operations on rational expressions, multiplying, dividing, and adding and subtracting. There'll be a few practice questions to go along with this in the Google Classroom, and that's all I have for now. Thanks for watching.